All right, my name is EJ Daigle, and this will be our second lecture. I'm going to kind of come back to an intro because we're coming back after the midterm exam and give you guys a little bit of a reintroduction and a fairly good review of some of the real basics and also some of the more important things that we need to discuss for CNC manufacturing. All right, so an introduction to CNC lecture. Here we go. So as a reminder, as you're looking at the controller on a CNC machine, what the controller on a CNC machine is essentially doing is it's sending commands to a motor to actually physically move that cutter using different geometries. So we have two types of codes that we use in our programming language here. The first is a G code. The G code deals more with the geometry of the CNC machining itself. So cutting motions such as linear or circular interpolation, what type of coordinate system we're using, tool compensations, things dealing with the motion of the cutter, and so that we know where the tip of that cutter is in space, in three-dimensional space at any given time. The M codes, on the other hand, deal a little bit more with the configuration of the machine. At least this is the way I've always thought about them. Now there's some things that, this affects an M code, affects a G code affects an M code. But generally speaking, M code is more dealing with the machine itself. So as an example, starting and stopping the program, starting and stopping the spindle, whether we're going to spin the spindle in clockwise or counterclockwise, tool changes, turning coolant on, things like that. The things that the machine really is going to control. It's a little less concerned with geometry and much more concerned with turning things on and off in support of cutting. All right, so let's get into a little bit about feeds and speeds. I want to make sure it's working here. So this is the chart that I gave you guys in class. You'll see we've got our feed and speed load chart here. And what we'll do is we'll just go through an example of doing some simple feeds and speeds. I'm getting a piece of scratch paper out here as well. I know we've done this a few times, but it will be important for us to just go through here and kind of figure this out as we can do this. So let's go through our particular example. Let's say we're going to do some cutting, and maybe we're milling a slot or milling the profile of a part, and we're using aluminum with a 1/2 inch end mill. So we know a lot about what's going on, and I guess I didn't include in here, we should probably also include how many flutes are on that end mill, right? So let's discard that for a second. 1/2 inch 4 flute end mill. See, I didn't put that in my original PowerPoint there, so let's get that in there. All right, so now we go back and we can look at we've got two equations here that we're going to use. The first one is our RPM equation, and the second one here is our inches per minute. And these are what we call our speeds and feeds. So the speed itself, again, deals with the rate at which that cutter is turning. So as an example, in a milling application like what we're doing, or a drilling application for that matter, it is the speed at which that cutting tool is turning in the spindle. So it's really the speed at which the spindle's moving, which determines the speed at which that cutting tool is spinning, the revolutions on that cutting tool, revolutions per minute. The other thing that we concern ourselves with is the inches per minute. So that is how fast we're going to feed that cutting tool into the material. And I always like to think of it like a hand drill. Everybody in their garage has used a power drill, a cordless drill or something like that. Well, there's two things you can do with a cordless drill too, right? You can pull that trigger at different speeds. A lot of them have analog triggers where you can pull them a little bit and they go slow, and you pull them all the way in and they go really fast. That'd be your RPM. But the other one is the inches per minute. How hard do you want to press this thing down into the material? It goes without saying, there's lots of things that determine that, right? Things like, what's the diameter of the cutter, right? So if I'm using a little 1/8 inch drill in my cordless drill and I try to feed it too fast, I'm probably going to break that drill. But it also deals with the material as well too, right? It may be different if I'm drilling into wood or if I'm drilling into stainless steel or something like that. So at that point, it becomes pretty obvious as to what we're doing. So now we just got to think, okay, what are we going to do first? Well, first thing I'm going to do is I'm going to calculate the RPMs. So let's go back a screen here. Aluminum, 1/2 inch 4 flute end mill. All right, so when it comes to that, we need to kind of say, okay, if we're going to be milling, we've got our feeds and our speeds. All right, and first thing when I look at that RPM equation, I've got it written up here as well, is cutting speed. I know the diameter of my tool, right? So the diameter of my tool is pretty easy. If I want to go RPM equals cutting speed, I don't know what that is, times 4 over the diameter of my cutting tool. We said the diameter is going to be 0.5, so I'll say 0.5. So that is going to, I've got part of my equation in here now. Now let's go back here. I see that I'm missing this cutting speed portion of the equation here, right? So that's a variable I'm missing right now. But as I come down into the cutting speeds part of the chart here, I can see what it is for aluminum. And if I go aluminum, well, I can drill, I can ream, I can tap, I can counterbore, I can bore. But if I go over to milling, here's another thing I didn't tell you. For all practical purposes in this class, we'll just assume, unless I tell you differently, we'll assume high-speed steel, and we'll assume roughing in this case too. So if I say that, I now know it's 240 is my cutting speed. So now I can go back forward here and I can say, okay, well now I know everything. I know that RPM equals 240 times 4 over 0.5. And I believe I've got my calculator programmed in here. Oop, gotta go back, or let me see here real quick, get back into here. Oh, there we go. Well, that does bring up the calculator, but it advances my slide, unfortunately, too, so that's not real handy there. All right, 240 times 4 over 0.5. All right, now I can do that real quick. We'll go 240 times 4 equals, divided by 0.5. So that's 1920. So I can see now that my RPM is 1920. Okay, so that's pretty easy. Now when I get into the inches per minute, which is my feed rate, again, this over here was my speed. Okay, this is now going to be my feed. How fast do I want to feed material into that cutter? Well, that's pretty easy to calculate as well. So inches per minute. And I will warn you that you know, when you look at this chart that I give you, this isn't necessarily a perfectly exact science. These are recommended feeds and speeds, right? These are recommended feeds and speeds. It doesn't mean that you can't go faster. It doesn't mean that you can't go slower. These are probably a good ballpark. And if you need to speed up or slow down a little bit because you're trying to meet a cycle time or something like that, all of that stuff can be varied and played with. I would even go so far as to tell you, beyond just the difference between carbide and high-speed steel cutting tools, you may have different quality of cutting tools too, right? You know, you can go buy a, you know, I don't know, you can go buy a Craftsman tool, you know, at Sears, or you can go buy a, you know, a Pittsburgh tool at Harbor Freight or something. And even just, you know, on like a socket wrench, you're going to have different qualities of tool. You'll see the same things with different vendors that make end mills as well. All right, so now I need my inches per minute. All right, what do we need for inches per minute? Okay, inches per minute, we need the feed per tooth, the number of cutting teeth. Okay, that's the N is the number of cutting teeth. And then we need the RPM. Well, we have the RPM, so that's good. Inches per minute equals the feed per tooth times the number of cutting teeth. Well, we have the number of cutting teeth, don't we? The number of cutting teeth is going to be 4, let me get that in here, times the RPM. So I've got most of this stuff set now. The only thing I don't know is that feed per tooth. So let's go find out where is that feed per tooth. All right, so I can see that here's my feed per tooth for end mills. Well, this is kind of where I want to be, right? I also have some feed up here rates if I was doing drilling or counterboring or reaming, but obviously that's not what I'm doing. I'm not using a drill, I'm not using a ream, I'm not using a counterbore, I'm using an end mill. And now I also know that I'm using aluminum and I'm using a 1/2 inch. So therefore my feed per tooth is 0.005, so what it's going to be. So we'll go back forward, and inches per minute equals 0.005 times 4 times 1920. I'll hit my calculator. 0.005 times 4 times 1920. Now to get 38.4 is what I get. I should check that math once here real quick. Inches per minute is 38.4. And remember what these are. I don't have to define it, but this is inches per minute. And this is revolutions per minute. That is your feed and your speed, or your, in this case, your speed and your feed rate. All right, so now that we have that, I'm just going to do that math one more time. I like to check that. 0.005 times 4 times 1920. Yep, 38.4. All right, so now let's talk about what our different codes do. You know, we've got a number of different codes. I'm going to get off my page here and talk about some of these different codes real quick. So when we talked about G01, we did that a little bit before the break. What G01 means is essentially means linear interpolation. If I define 2 points in space, like if this, if I have a coordinate system here, and you know, this is 0, 0 here, right? And I say, if I call that G01, and I say x 0.0 and y 0.0, that's my starting point. And then I don't need to redefine G01 again. That we call that that term modal. What that means is I can turn it on, and it stays on until I tell it to do something else, until I turn it off, essentially. So I'm going to stay in G1 mode until I tell it not to be in G1 mode anymore. So since I didn't tell it to do any other things, I'm going to say, well, now I want to go to x 1.0 and y 1.0. And so if I do that, and if this is 1 and 1, then this will be x 1.0, y 1.0, right? So 1.0, 1.0, and down here was 0, 0, essentially. Linear interpolation, because of this G01, means that all I'm going to do is I'm going to draw a straight line between those 2 points. Now that would require me to actually be able to draw a straight line, which apparently I can't do. Let me try doing that one more time with a little better line there. All right. And we'll go to pointer options and go to a pen again. There we go. Let's go down. Well, there you go. It's a straight line between those two cutters. So I'm going to mill in a straight line between those two cutters. So what I'm going to do. When we talk about a G02 interpolation, what we're really talking about is the ability to create a circular arc. And as soon as you see this CW, we're talking clockwise. And CCW means we're talking counterclockwise. So as an example, if I drew up, again, a nice little graph here, a nice little coordinate system, we'll call it, right? Here's my X and my Y axis. There's X and there's Y. And let's say I go out 3 places now, 1, 2, and 3. And I'll go up 3 places, 1, 2, and 3. And let's say we go G01, X 1.0, Y 1.0, X 1.0, and Y 1.0. But now we're going to turn off G01 and we're going to say G02. So what we really did was wherever we were at, so let's say we're at 0, 0, we took a linear interpolation to 1, 1 is what we did. And we landed here is what we did. So maybe we went like that to get up there, right? Linear interpolation. But now we turn on G02. We know that G02 is a clockwise circular interpolation is what it is. And we're going to have to give it one more command. We're going to say, you know what, I want to go to X 3.0, Y 3.0. We'll just say X 3.0 and let's go Y 1.0, excuse me, and Y 1.0. So we're going to go to this location now is what we're going to do. But we're going to use a circular interpolation in the clockwise direction. Clockwise direction again means we're going to go this way like a clock would rotate. And a counterclockwise direction would be we're going to go that way, like a clock would rotate. So that's clockwise versus counterclockwise. We need one more command to give it. And we can do this either with an IJ or we can do this with just a radius. I'm going to stick with a radius for today just to show you the simplest method here. We're going to call this radius of 1.0. What that means is it's going to create an arc with a radius of 1.0 to get there. So if I kind of think about this, I kind of set it up in such a way that if I called this the middle of a circle that would go around this, let's say, right? A circle that would go around this. Well, I can see that it is 1 in between these things. So I'm going to create an arc that goes radius 1, and we're going in the clockwise direction. So we're going to go like this all the way over to here. And what you'll notice is that the radius equals 1. The radius is the distance from the center to the outside. That radius equals 1. And so if I'm doing that with a clockwise interpolation, Obviously, it's going to look like that. Let's change colors for just a second, because again, this was 1 and this was 0.3, right? Let's go ahead and change colors with my marker here for a second. We'll go to pointer options and we'll go to color. We'll try to do this in a different color so we can see a different result here. And now let's do the exact same thing. Let's say that we did G01, X 1.0 and Y 1.0. But now instead of a G02, we're going to do a G03. But we'll go to the same locations. We'll say we're still going to go to X 3.0, and we're going to go to Y 1.0. And we'll still do that with a radius of 1.0. Well, what does that look like? Well, again, we started off down here and we took a linear interpolation up to here. Apparently, I can't draw a straight line to save my life. But now we're sitting here, and now we need to go, this was clockwise up here. This is going to be the counterclockwise version of this down here. So now instead of going up and around this way, we're now going to go down and around this way to get up there. You'll still notice that we still have an R, a radius of 1, right? The distance between 0 and 1 on the y-axis. So we have a radius of 1. And you can see how I could vary that radius. And by varying that radius, I could make a bigger radius curve, or I could make a shallower radius curve by just varying that radius number to get to that other point. So if I was using a different radius curve, there's a number of different radii I could use to get there. I'll use a different color altogether here. Could I still go in a counterclockwise direction but with a less of a radius? Sure. Could I go to a counterclockwise direction with with some sort of bigger radius? Probably. Whatever that might look like to get there is what I'm going to do. All right. So now let's move on a little bit more. Let's talk about creating a toolpath. And so I'm going to keep this fairly simple right now as far as what we're trying to do. And I do want to go back for a second on this here, because even on some of these, it may be required to actually redefine, where did I go there? There we go. You may notice when you're creating programs like this, you may actually have to define intermediate points. This curve's real simple, but this curve is a little bit more complex, and there may be intermediate points that define radius in between those parts of the arc as well. So I don't want to make it as simple as I maybe laid it out there. All right, let's start off with a simple toolpath. This will be similar to the homework or lab exercise I'm going to be giving you guys to work on. Let's talk about what this looks like. But before we do that, that is going to be our toolpath. Before we do that, we want to talk about getting into that G&M code. And I know we've talked quite a bit about this before, but just as a good review, because it has been all the way since back before the midterm exam, which was a while ago, let's talk about what each one of these things means, okay? First off, every program we write is going to start with the percent sign. Okay, just done. Don't worry about much with that. Just know that that's what's going to be there. The next thing that we're going to do is we're going to give our program a number. And again, we are talking about a Haas controller. So that's what we're dealing with. So some of the stuff that you'll see in here will be specific to Haas. Much of the stuff that you see in here will be, the majority of the stuff that you see in here will be not specific to any particular vendor. G&M Code tends to bounce between the different controls very, very well. It's like driving a Ford or a Chevy, right? So what I've got now is I've got my program number here. Notice this is an O, and then this is 0001. And what I have over here are what we call human readables. Everything in the parentheses is what we call human readable. That means it's a comment. It's a programming comment for the programmer or for the person reading it. It is not part of the actual code. So the machine doesn't care about what's in the parentheses. The machine only cares about what's over here, right? All right, let me get an eraser up here real quick. That got kind of messy there. Sorry about that. All right. So we know what the machine reads, and we know what the human is going to read, and that's really what we're concerned with right now. All right, pointer options. Go back to my pen. All right, so we got our program number. We got the percent to start the program. The next thing we have here is we have T1M6. I did give you guys a nice little set of notes that you guys can look, or you can, Google Haas G&M codes, and you can find them almost anywhere. But if I look in my manual here, what is M6? Maybe I don't know what M6 is. M6 is a tool change. And what we're going to do is we're going to do a tool change to tool number 1. So I made a note of that, but again, this is the only thing that the machine needs to know. It says, okay, I'm going to go grab whatever tool is in tool holder 1 or in the position 1, and I'm going to plug that into the spindle, and I'm going to start making chips with that part. The next line of code is our safe line. This is a very important line of code. If you don't remember what the safe line does, what it really does for us is it puts our machine into a known set of conditions. So it's very important. Are we an incremental? Are we an absolute? There's all kinds. Let me go through some of these. So like a G00 is going to be my my rapid motioning position, and that's what we'll use initially to just get around until we define linear and things like that. We're going to worry about the feed rate. G17 is my XY plane selection, so that's actually telling me what plane I'm going to work in. G20 is I've actually selected inches. If I wanted to select metric or millimeters, I would work with the G21, but we're going to work in inches. G40 is cutter compensation cancel. So what that means is any cutter compensations that are in the machine right now, we're basically going to negate and default those out, and we're going to recall those and build those ourselves. So we want to cancel those out. G49 is a G43, G44, G140. 143 cancel, but this also deals with some of the things like cutter compensation, tool length compensation, things like that. That's what the G49 is. Oop, I keep bouncing on my slides there. Sorry about that. That was the G49. The G54, that's going to select my work coordinate system. So my XYZ work coordinate system. And we are working with based upon that, kind of goes hand in hand with that G17 where we select the XY plane that we're going to work in. And then this will be kind of our XYZ coordinate system. G80 is going to be can cycle cancel. So this is just canceling out some things that may have been called. We have some can cycles like drilling cycles and things like that we can turn on. And they are modal in the fact that if we didn't know they were on, the machine would just start up with them on, but we want to make sure we're setting those to a known position. And then this will be absolute position, the G90. That's an important one. Remember, absolute means that I'm going to call out, as an example, X 1.0, Y 1.0, and that's how I'm going to know if I'm going from 0. Let's say I'm going from 1.0, if I'm going from X 0.0 to Y 1.0. In absolute, I'm going to call out both the X and Y, even though the Y didn't actually change. In incremental, I'm only going to call out the change in motion that I'm making. So if I'm moving across the X-axis in 1 inch, or then I'm only going to call out that X 1.0. I don't need to call it Y. I'm just going to stay in that axis. We're going to tend to stay in the absolute. There are times where incremental makes sense, but you can build up some stacking of error. So we're going to call every position out with its XY location. So we will be in X absolute. The next thing that we'll do is we will select our work coordinate system 1, which is G54. We are going to go to a location, which is going to be 1, 1. So we're going to take our spindle, we're going to put it up above at the X1, Y1 location. What that means is the spindle is going to be sitting right here, ready to go, above the workpiece. We're going to set our speed. It's very important. I didn't tell you what material we're using for this, but in future examples, this will be your speed calculation. This is where your speed calculation will go. That's your RPMs. So you need to know what material, how many flutes, the diameter of the cutter, things like that. Then we're going to go into our M03 code. And again, our M03 will be our spindle commands. All right, so turning the spindle on, so on and so forth. Then we'll go down to a G43. A G43 with a height of 1. So G43 is actually our tool length compensation. So it's important for us to know how long that tool is. If we don't know how long that tool is, we don't actually know if we're cutting. Meaning if I tell it to go down, down in Z 1/2 inch, and I think the tool is 2 inches long and it's actually only 1 inch long. It doesn't matter if I go down in Z negative 0.5 or not, because it's never going to reach the part because my tool isn't that length. So it is important that we know how long that tool is. And then once we do that, we are going to take Z 0.1. So we're now hovering at this point on the XY coordinate system, 0.1 above the workpiece. At that point, we're going to do G01, which is a linear interpolation. So we're no longer in rapid, we're actually going down at a feed rate. So now this is our feed calculation that you guys built. So now when we're at the rapid rate, the G00, it's essentially telling the machine go as fast as you can go. I'm not cutting through material. I don't care about aluminum or cutters. I'm not even hitting material. I'm going to go as fast as I can go. That's going to decrease cycle times and so on and so forth. But now we are going to call out a G01, which requires us to put in a feed rate. So we do need a feed. So our feed rate comes from our calculations on the previous slide, 10 inches per minute. And now we're going to cut into that material a 1/2 inch. So Z minus 0.5 means not only are we working in X and Y here, but now if you're looking at that cutter going down into the workpiece, we're actually going to cut down into that workpiece 0.5 inches is what we're going to do. So if this is the flat top of the workpiece, and this is Z minus 0.5. So imagine turning this axis on its side and kind of looking at it just from the Z side. All right, so that's going to be the chunk of code that we need to start our program, is essentially what we need. So I'm going to go ahead and grab that code real quick. I'm going to discard those annotations. We don't need those right now. And I'm going to grab that chunk of code. And what I'd recommend is you guys could do the same thing. If you want, you can just type that code in, pause this for a second. It'd take you literally seconds to type this in. Post that in NC Viewer. I'm going to plot it. It's not going to do anything. So I went to ncviewer.com. This happens to be the one that I like to use, ncviewer.com. It's a great tool that you can use to just look at your tool paths and just verify that it's doing what you think it's doing. You'll notice my code is over here, and I know there's a way to change that font size. Let me do that here if I can. There we go. And I'll move this, maybe I can move this over a little bit too. So I can see I've got all that code that we just typed in here. When I hit plot, nothing's going to happen. The reason why nothing's going to happen is we don't actually have any toolpath going on, right? I would assume if I actually had this over far enough, I could see that my cutter is actually at 1,1. So if I highlight line 6, I can see the cutter is at 1,1, but I'm not actually making any parts yet. And that's because all we've done is we've set up the machine. We've said, okay, machine, here's where I want you to be. Here's your speeds and your feeds. Here's all of the can cycles and your tooling compensation, all that stuff that we're going to get into the machine. But now we need to physically go in and build the code to make this thing. All right. So we're starting off at 1,1. And let's talk about what we're going to do. Okay, so I'm starting off right down here at 1,1. And I probably didn't need to call this again because I'm already there. But I've dived down into the part, because I dived down into the part right here. I was already at 1,1, and I dived down into the part with Z minus 0.5. So I am cutting into this material at 1,1. Now it's up to you which way you want to go. You can tell which way I went. I didn't go this way. I went this way. What I'm going to do is I'm going to cut across this part in this direction. I've already called G01 from the previous line of code. And we remember G01 is modal. I don't have to call it every time. So I certainly could write G01 in front of every single one of these, but there's no sense in doing that, right? But I need to go all the way over to 8,1. That's my next point. I'm doing that in a linear motion. That is my tool path I'm taking, a straight line. And I'm going to go over to X 8.0, Y 1.0. Done. Now, without even looking at this stuff on the left, don't look at the code. Look at what we're doing instead. So here was X 8.0, Y 1.0. That's what got me there. My first point was X 1.0, Y 1.0. Because I'm in absolute, not incremental, I'm calling both points every single time. And now at this point, I'm gonna scroll up to this point. I need to go to X 8.0, Y 5.0. Well, guess what? The next thing you're going to see in here is X 8.0, Y 5.0. Then I'm going to go all the way across over to here. Right, this is the direction of travel this way. I'm going to go to X 1.0 and Y 5.0. And then I do want to cut this path too. This is part of my tool path, so I don't want to stop at this point. I want to make sure I continue cutting. So I'm going to cut down back to x 1.0 and y 1.0. So you'll see that again. So there was my 1.5 and there was my 1.1. All right, now it's important for me to go and start cutting the interior of this thing. So now I want to cut, I don't want to cut across. There's no need, I don't want to cut across here, okay? Because that's not a tool path. I just want to cut this, this profile of the tool path here, and then I want to go follow this line. Basically, we're connecting dots is all we're doing in these particular chunks of code here. So because I don't want to cut the material, I want to lift my part or my cutter up out of the material. So what you'll see here is you'll see a G00. That is a rapid to Z0.5. What this does is this gets the cutter out of the workpiece. So cutter above workpiece. So that's what we're trying to do here is just pull it out of the workpiece. I don't want to mill through here. I just want to take a path to here without milling. And I want to get to 3.2. I'm not cutting at this point. All right. So I went up, and now on the next line I'm taking a linear. And by the way, when I went up, I actually went up rapid. I went up as fast as I could. And now I'm taking a linear path over to x3, y 2.0. That's this. This is x 3.0, y 2.0. Perfect. Now I'm going to go ahead and bring the cutter back down to the part with a rapid. I'm going to go down z minus 0.25. So I went back down into the workpiece now, and now I'm going to start cutting again. Now there's two ways I could go. Okay, I could take a linear path, a G01 over to 6.2. I can tell you that's not what I did. The reason why I know that's not what I did is I look at this next one here. Instead of going over to 6.2, I actually went over to 3.4, didn't I? You can see 3 and 4 there. So I actually went over to here. So what I'm going to do is I'm going to take a radius, some sort of, notice what direction we're going. This is a clockwise. That's a clockwise direction. And I know that the radius is 1. Well, how do I know the radius is 1? Well, there's a couple ways to know, right? This is on my y here. Oh yeah, I guess I'm fine. If this is y4, then this is y2. Then this must have a radius in r of 1, right? r equals 1. I don't want to include that in there because that's going to make us think that we've got a cut there, but that's not a cut. But it is a radius of 1. All right. So what you'll see on that next item there is you'll see that what I did was I took a clockwise cut from 3.2, which was right here, and I did a radius of 1 up to 3.4, which is right here, which will take me right along that edge precisely the way I want to do it. And I noticed in my print it did actually give me radius 1, so I actually knew what that radius was. Next I'm going to go over to 6.4. So I've got my cutter in the part still. I'm going to go all the way over to 6.4. So this will be x 6.0, y 4.0. And I know I need a G01 to get there. So it's a G01, a linear interpolation over to 6.4. That looks good. And then I need to go from 6.4, which is here. I need to take another clockwise, notice the direction there, it's clockwise interpolation over to 6.2, which is x 6.0 and y 2.0. So I see a G02, x 6.0, y 2.0, again with a radius of 1. Now we didn't draw in the radius on both sides, but I will tell you in this particular case, I will assume the radius to be the same on both sides. And that might be an assumption I may not always want to make, right? Then the last thing I need to do is I need to get from 6.2 all the way back over to 3.2 in this direction. So I can see a G01 that goes from x 3.0 to y 2.0. And then the last step here I'm going to do is I'm going to do a G00. It's going to rapid me out to just above the workpiece, which is a ½ inch above the workpiece. I'm pulling my cutter out of the metal at this point. I'm going to do an M09, which is I'm going to turn the coolant off. I don't remember if I ever turned the coolant on. What did we do here? We did a M6 tool changer and M3 spindle commands. I don't know that I ever turned the coolant on there. But anyways, so I'll make sure the coolant is off now because I didn't see an M8 up there anywhere, did I? Probably should have turned the coolant on. One thing to note, you might have noticed this down here. In the NC simulator, you can put as many M codes on a line as you want. I will tell you that's going to cause you grief when you go to download to the Haas machine. It only allows 1 M code per line, so be careful. So I'm turning the coolant off. Should have turned it on before. Here, I turned it on up here. How's this? M08. Coolant was on now. Now the coolant's off. M05 is another spindle command. I'm gonna turn that spindle off. And then my M30 essentially marks the end of my program and resets the machine so that it's ready to run again. So hopefully that makes sense to you. Again, at this point, my only goal for everyone is to make sure that they understand, G01 versus a G02 versus a G03. They can do the feeds and speeds calculations. They understand the absolute positioning, where we're doing X's and Y's versus incremental positioning. And I think everybody should be able to do that at this point. So what you're going to see this week is you're going to see a couple of prints. Let me see if I've got it up here. I think I've got at least one here. When you're working on this week's homework, what you're essentially going to do is there will be a worksheet that will look something like this, and it's gonna ask you some questions about and I may actually change some of this, so don't get too fed up on this. It's actually going to ask you some basic questions, and you can just type in your answers, in here. Save the Word document. You can email it to me, and I can work off that. Same with here. You can type in what is G02, what is G03, what are all these different things. Down here at some point, it's going to ask you, things like, just make sure I keep my document formatted here. What is the purpose of a safe line? I think you can go back and review the video or the notes from prior to the midterm. Describe the purpose of each element in this safe line. Calculate the feeds and speeds for a particular part. Then I'm going to give you a part that I want you to make. Now you can assume by looking at this, you can kind of tell where we're at. This is 0, 0. This is X5, Y4. So you can tell what the radius is on every single one of these. I made it fairly simple. And I don't care which direction you go. Just realize if I go this direction, I'm probably going to do a clockwise interpolation. If I go this direction, I'm probably going to do a counterclockwise interpolation. And I'm fine with any of that. You will have to calculate your feeds and speeds. There's your material and your tooling. And then all I want you to do is paste your code right here. Because what I'm going to do is I'm going to take your code, once you've pasted it in there, I'm going to go ahead and paste your code into NC Viewer. And let me I should do this while we're in here. I wasn't thinking about this a minute ago. Here's all the code we just went through, right? Let me grab that code and let me paste that into NC Viewer and see if we can see what happens with this. So this is the part that we were just making a few minutes ago. And you can remember what it was supposed to look like. This is what it was supposed to look like. And we're not supposed to cut between, right? We've got like an outside profile that's rectangular, and then we got this inside kind of racetrack profile that we're cutting. So now I'm in NC Viewer, and I can test this. And you can do the same with your code too. So don't feel like you're writing this with no idea of whether or not it's going to work. Write it with the idea that you can test it. So when I hit plot, I can actually see what's going on. And I can go to my individual lines. There's line 8. There's line 9. I can see where the cutter is as it's moving around. Line 10, line 11, and back to the start. Now notice what happens when I go to line 13. The cutter comes up off the workpiece so I can travel across and not be cutting. And then I go back down into the workpiece. And by the way, I'm at a different depth on that inside racetrack than I was on the outside profile. And then I'm going to bounce around. There's that radius. There's that straight. There's that radius. There's that straight. And then back up and out of the part. And then I'm done. And you can see if you turn it off by the red button and then you hit plot, it'll actually plot what that toolpath is going to look like. So your goal for this week, you will do a worksheet, homework, which will include some questions, and it'll be on this particular worksheet, not this one actually. It'll be on this particular one, where it'll ask you some questions up front. For a few questions for sure, you'll have to answer all those. Then you'll have to write the code for this particular toolpath and paste that code in here. All right, and then save that as a Word file so that I can clip your code out, and I can and make sure it's not a screenshot of your code. Make sure it is actually the typewritten code. You can put a text box in there if you want, or you can just paste the code right into here. That way I can just copy it, paste it out, and test your code. And then you can save this file with your name on it. You might call it week of 330, Johnson, or whatever your last name is. Email that over to me as your homework. And then we should be good. The other thing that I will also do this week is I will also have a quiz. So number one, watch the intro video. You've watched this video lecture. You've done the homework assignment for the week. And then before Friday, you've taken the quiz. I'm going to try to be really lenient with you guys at this time, just with all the stuff going on. I'm assigning everything first thing on Monday again, but nothing is going to be due until Friday at 11:59 p.m. So that gives you a full 5 days time to work on this. So please feel free to email me questions or concerns that you might have along the way. And with that, I hope all of this helps you. And feel free to watch this video and pause it wherever you need, even if you have to pause it on the feed and speed chart or whatever you might need. I did share this with you guys earlier in the semester as well, though. So on that, thank you, and I'll get this posted onto YouTube.